Okay, so we've been talking about lines and planes in R2 and R3 respectively. So now we're going to talk about a kind of related idea, but it's a little bit of a mix and match. So we're going to look at lines, which we have looked at before, but in R2. But we're going to look at them in R3, where previously we had only looked at planes. So how are we going to go about doing this? There's a temptation to say, well, let's just take a line. If you want to describe the line, then just give me a vector perpendicular to it, and we'll play the same kind of game that we did previously, right? And here's a big problem. If you have a line in R3, there's lots of vectors perpendicular to it. There's a whole plane perpendicular to it. Right? So that's not really a good way to go about this. To describe a line in R3. So what we're going to do instead is just a little bit of a different geometric foot in the door. We're going to say, I'm going to describe this line. I'm going to characterize the line by, well, give me a point on the line and a vector parallel to the line. And again, I'll note that here there is a unique line, right, that is that goes through that point and that is parallel to that vector. Everybody on board? This is more crisp way to go about doing this. Yeah. Oh, yeah, I'm sorry. I completely forgot. Yeah, homework's due today. Yeah, and thank you for reminding me. Yeah, so it's due at the start of classes. Let's see here. Here, I'll move this out of the way. How about this? Today only. Let's just wait till the end of classes so we don't have a big moving around of people and stuff. But make sure to remember before you leave, maybe right up here on the front corner of the desk. Thanks very much for Okay. Right. So this point and that vector are a way to characterize that line. Okay. Now, how do I turn that into algebra? Well, we're going to do a similar game. I would like to decide whether or not a point, some given point, either is or is not on the line. Here's the two possible cases. Notice that this is or is not on the line is decided by whether that difference vector is either parallel to the line or not parallel to the line. Right? So the point x is on the line if and only if x minus x naught is parallel to the line. But of course, parallel to the line means parallel to the vector v. Parallel means that it is a multiple of v. Right? And then we can, I'm going to say, solve for x in this equation, and that gives us this expression right here. So every point x that is on the line has this form. Every point on the line must look something like this. It's x naught plus some multiple of v. All right. So this is it's tempting to call this the equation of the line. We can't technically quite call this the equation of the line. Let me explain the problem with calling this, the equation of the line. An equation is supposed to be a test. Right? Something like this, for example. So if you come to me with a point x comma y, I plug in the x, I plug in the y, and then I look at the equation and ask, is the equation true? The equation's true? Yes. If the equation's not true, no. Okay. That's not what this is. Right? So I know what x naught is. X naught is let me color code correctly. X naught was given, v is given. Those are my descriptions of the line. So if I come to you with a point x and plug in that point x, can I decide whether this equation is true or not? Well, not really, because I don't know what t is. Right? So this algebra that we have written down here is not a test of whether x is on the line. If I plug in x, I don't get a crisp answer. If I plug in x, I get an algebra problem of does there exist a t such that blah, 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 blah. Right? So it's does not play the same role with the line that equations played in our previous context that we considered. Okay, so we give it a different name in recognition of this. We call this a parameterization of the line. And parameterizations have a nice alternative interpretation. Equations of shapes are point testers. They very crisply decide yay or nay, is it or isn't it on the line, right? Parameterizations are point generators, right? So specifically, again with the understanding that the x naught is given and v is given, I can take this t, I can plug in any value I want, and out comes a point on the line. I can plug in different values of t. Cool, I keep getting more points on the line. It's a little point factory. Everybody see what I'm talking about? So it's not so good for testing points, but it is really good for creating points on the line. Okay, so different algebraic tool there. All right, so easy example. Suppose I want to parameterize a line that passes through these 2 points. So I've got 2 points on the line. Notice that if I have 2 points on the line, then their difference is parallel to the line, right? And so I can use either A or B as my x naught. I can use that difference vector as my direction vector. And I've got everything that I need to parameterize the line. And you can see that's what happened here. These two, the A and the B, you subtract to get that direction vector. Right, and then pick, again, doesn't matter, pick whichever one you want, either A or B to be your x naught. Looks like I picked A for no particular reason. Okay. All right. So I like this next example. I think this is a nice way to illustrate the difference between equations and parameterizations of curves, of geometric objects, I'll say. So let's suppose I want to find an intersection. So I want to find a point that's on the line described by that parameterization, but that is also on the plane with that equation right there. So I've got a line and a plane, and now geometric appeal, if you have a plane and a line, but generically, we're going to ignore the case where they're parallel, right? But generically, if you have a line and a plane, you expect that they would intersect, and they would intersect at a single point. Okay. So let's find that point of intersection. Okay. So we have two different kinds of algebra. We have a parameterization of the line. We have the equation of the plane. How do we make these sort of fit together? And the nice observation I'd like to make is I have a point generator and I have a point tester. And what I'm going to do then is I'm going to generate points, and then I'm going to test them, right? And that will be the way that we'll find what we're interested in. So let's get started on the details. The way we're going to do that, first of all, let me rewrite what this says here. If I were to look at one coordinate at a time, I have 4 plus 3t, 3 plus 0t, and then 1 plus 3t, right? That's that parameterization, just written kind of all together as a single vector. Keep in mind that means that this is x, and that is y, and that is z. So this parameterization is generating any value of t that I plug in. It is generating a point x, comma y, comma z. There are the formulas. And then I want to test and see, all right, well, if I take this x, this y, and this z, here's how I would then decide whether that x, y, z satisfies this equation. I would take those x, y's, and z's, I would plug them straight on into that point tester that we have, and then if the equation works, then I found a point that is, in fact, on that plane. So what I'm doing is I'm generating points that I know are all on the line. I'm then testing to see which ones are also on the plane. So said differently, once I plug this into there, all I have to do is solve for t. Right? Okay, so notice, question.
And what could the t represent?
So t is, there's different ways to think about it. I'm going to talk about that more in the next few lectures. But for the moment, t is just a way of recognizing that if something is parallel to v, then it must be a multiple of v. So for the moment, it's just this raw material input that goes into our point factory that decides what multiple of v generates the point x. Yeah. Right. Okay, so we take those x, y, and z, plug into that equation, and out comes this equation. You'll notice that from my parameterization, here's the x and the y and the z, and I'm plugging that into this equation that says x plus y plus 2z equals 0. Multiply it out, collect terms, solve for t. T is -1, and that value of t, plug it back into your parameterization, and it generates this point. So that is the unique point, that is that intersection. Okay. All right. Okay, so parameterizations a little different. Again, these are point generators, not point testers, and sometimes that's handy. Sometimes it's good to have point generators. By the way, we're going to do a lot with parameterizations in this course. It's hard to see it coming, but it's good. It's going to happen. But sometimes we need a point tester. Right, so the question I'd like to ask now is, given this point generator, given this parameterization, how would I construct a test to decide if, you come to me with a point x, y, z, is it or is it not on the line? How do I decide? So here's the idea then. Here is the parameterization. Right, so base point x naught. T times a vector v. V may have, let's say its coordinates are called a, b, c. So this is the parameterization. I would like to know if, given a point x, y, z, I'd like to know if that works. What we are actually asking then is there a value t that I can plug in that generates that point? Right? That's what I'd like. Is there some value t that I can plug into the parameterization, and what comes out is the point that I'm interested in deciding, if it's on the line or not. So, is there a value of t? This is actually a pretty easy question to resolve. If there's a value of t, I know exactly what that value of t has to be. That value of t, solve that first equation, that value of t has to be this. No question. Right? I mean, it just has to. At the same time, that value t also has to be that. And furthermore, that value t had better be that. So this value t that I'm hoping, fingers crossed, I'm hoping that there's a value of t that'll generate x, comma y, comma z. That value of t has to equal to all three of these things. Now, under what circumstances is it possible that there could exist a single value of t that equals all three of these things? And the answer is that value of t can exist if and only if these three things are equal to each other. If these three things are equal to each other, then good news, that's what t is. That's the t that generates the point you're interested in. If these three things down here are not equal to each other, then there is no single value of t that's going to simultaneously generate all of these things. You need different t's for different coordinates. That's not how a parameterization works. Okay. So this is the point tester right here. You give me a direction vector ABC. You give me a base point x naught, y naught, z naught. Here's how I test. If you give me x, y, z, I plug into this kind of three equations, if you will, and I make sure that all three of these things have to be exactly equal. If they are, great, we're on the line. If they're not, nope, sorry, not on the line. Okay. All right, so these are called the symmetric equations for the line. There we go. Symmetric equations for the line. Easy to get to and from these two different forms, the parameterization and the symmetric equation. It's all centered around what is t, right? So if you want to get from there to there, solve for t, set the results equal to each other. If you want to get from the symmetric equations back to the parameterization, just notice that your symmetric equations, all three of those things are t. Solve for x, y, and z. Everybody happy? Okay. What I'd like to point out that I think is not a good practice, I'm going to say in Math 212, I'm going to say I have a policy against the following. What I don't want you to do is just sort of memorize the sort of the symbolic shuffling of characters and just notice, oh yeah, these things I'm supposed to put those here, and those things, those things I'm supposed to put down here, and that's how you do it. Please don't do that, right? There's no substance to that as an argument. So if I give you a symmetric equations and ask you to parameterize, I need to see the argument, and vice versa. Okay. Okie dokie. Easy example. All of these things are t. The t's that you get by solving for t in all three of these equations, or said differently, you can solve for x, y, and z in these other equations to get back to there. Yep.
So you're saying on the test, if we need these symmetric equations, we should first declare like x equals to x naught plus ta, and do that for y and z also?
So I want to see if you want to convert from one form to the other, I want to see the argument, just as I described there.
So you want to see the 3, 2, 5 plus t, negative 1, 1, 2.
I'm sorry?
You want to see the thing you just point the arrow to? Or
If on a test, if I give you a parameterization and ask you to find the symmetric equations, what I want you to do is solve for t in all three of these equations, right? And note that t is equal to all three of these things. So in other words, just what we did up here. Yeah, right. Okay. Okie dokie. Now, so these symmetric equations, you heard me say that there's three equations here, and I know y'all may be looking and saying, well, yeah, but hang on here. I see two equal signs. So it's kind of two equations, isn't it? And it depends on how you look at it. And I suppose, okay, maybe, right? But I'll point out that here's another way to think of those symmetric equations. These three things all have to equal to each other. And there are three pairs. When you look at three things and require that, pairwise that they're all equal, that is kind of technically three equations, right? Even though I suppose, if these are true, then it follows that that one is true too. Okay, but anyway, let's not quibble. Okay, so this is a different way to write the symmetric equations, and now I'm going to ask a next question, which is, what is that by itself? Right, so circled in green, we know that's the symmetric equations of a line. What geometrically is represented by this single equation in blue? Okay, this is a hard question. But it has a surprisingly easy answer. It's a series of observations that the answer is going to fall in our lap. First observation I'll make, this is a plane, because I can do some algebra and I could rewrite this as something x plus something y plus something z is equal to something. Right? That's just, whip terms around. I can make that happen. Side note, I do know that there are no z's in the equation, so that's not really a question mark. That's a zero. Okay, so I have a plane. Second observation I'm going to make. This plane, I claim, contains the line. Now, how do I know this plane contains the line? Well, let's think about, suppose I have a point that's on the line. If my point is on the line, that means that all three of these equations are satisfied. That's what it means for a point to be on the line. All three of those equations are true. Well, if that's the case, then that equation is true as part of that. Right? So what that means is that every point that's on the line is also on the plane. Therefore, the plane is contained inside of the. That's right. The line is contained inside of the plane, or the plane contains the line. Does everybody see what I'm talking about? So, in other words, we've got kind of this situation here. We've got a plane, and the line is embedded inside of it. Okay. Last observation about this equation here. The fact that there's a 0 there tells me something very important. Keep in mind, we established recently that these numbers in the equation for a plane, those numbers are the normal vector. That means that my normal vector for this mystery plane has a third coordinate, which is 0. So my normal vector, it doesn't point up in any sense. It doesn't point down in any sense. My normal vector is horizontal. And if you have a normal vector that is horizontal, that means that the plane has to be vertical. Now exactly how it's vertical, I mean, it can be twisted around, I don't know, right? But it's vertical. All right. So that actually tells us exactly what this plane is. There is a unique plane that contains the line and that is vertical, and that is what I like to call the shadow, the vertical shadow, or the Z direction shadow, if you will, of that line. Okay. Now I'm going to leave as an exercise for y'all to do on your own. It'll be analogous to the argument that we just made there, but think through for yourselves now, what is this equation? What does that equation represent? And I claim it represents the Y shadow of the line. Details to think through there, but the Y shadow means, okay, suppose someone was holding a flashlight, from over here in the Y direction, and that shadow that would be cast by the line is what that equation represents. Okay. All right. Likewise for the third one. Okay. So moving along, we're going to talk about coordinate systems now. This is going to be a quick section. For one thing, it's not very long. For another thing, this is pretty straightforward stuff. Nevertheless, do take time to read through and make sure you understand all the details that are in here. I'm going to start by talking about rectangular coordinates. We already talked about this a little bit, but given a point, there are these three coordinates that come about by looking at this box that you can make, this unique rectangular box. Okay. All right, so rectangular coordinates. This is not the only way to describe points in space. If you've got points in space, telling me X, Y, and Z are one way. But I could also give you different information to describe exactly which point I'm talking about. So, for example, now let's go down to 2 dimensions. We're going to talk about something called polar coordinates. So this point right here, I could describe it by telling you the X and the Y. That leaves no doubt exactly which point I'm talking about. Or, if I were to instead tell you this angle, thus describing a direction, and then if I were to tell you how far to go in that direction, again, that will uniquely describe that point. Right. Okay. All right, now I wrote this down here. I wrote this down as being a distance. That is a little bit presumptuous. It's not necessarily a distances are intrinsically positive. I'll point out that we really should. Oh, whoops! What did I just do there? We really should allow for the possibility that maybe r could be negative. In other words, in that direction, positive r's would be that way, and then negative r's would just be going backwards. It's like you have an axis system, and axes can have positive and they can have negative along that axis. So, okay. All right, but loosely speaking, we tend to think of it a little sloppily as being a distance. Okay, so a little bit of trigonometry, and again, exercise for you all to deal with on your own, but x is r cosine theta, and y is r sine theta. That's just a matter of looking at this triangle and thinking about trig. Note that that's a right triangle. So we have formulas for x and y, which I write like this. So x, let's see here. So x is r cosine theta, and y is r sine theta. Now let me explain my notation that I'm using here. You'll notice that I'm indicating with this subscript of r that that r there means rectangular. So this is saying the point whose rectangular coordinates are x and y. This, again, you'll notice this subscript, rectangular. So I'm telling you that the point whose rectangular coordinates are x and y, that's the point whose rectangular coordinates are r cosine theta and r sine theta. That's just a fancy way for me to tell you that x is r cosine theta, y is r sine theta. Now, on the other hand, what are these r and theta? Well, look at this. Here my subscript is p. That says polar. That says I'm talking about the point whose polar coordinates are r and theta. Okay. And so another way to say this is the point whose rectangular coordinates are x and y. That's a point whose polar coordinates are r and theta. And here's the conversion formulas between the two. Okay. All right. Some other formulas, and again, I have to correct myself a little bit. If r is positive, r is the square root of x squared plus y squared. Again, a little presumptuous. What I should have written down here is r squared is equal to x squared plus y squared. That's always true. R is not necessarily always positive. Okay, so let me scratch that off. And tan theta is y over x. Now, an analogous mistake that I could have made but didn't is I could have said theta equals arctan of y over x. Well, that's, again, presumptuous. Theta doesn't have to be a value of arctan. Arctan is only allowed to take certain values. Arctan is always between negative pi over 2 and pi over 2. Theta is not so constrained. Everybody happy? But tan theta is always y over x as long as x isn't 0. Okay, fine. Okay, we're going to do a lot more with polar coordinates later on. I just wanted to establish what polar coordinates are. Along similar lines, there is a coordinate system called cylindrical coordinates. Cylindrical coordinates pretty much means for any point in space, drop down to the xy plane. And we're just going to do polar coordinates in the xy plane. And then we'll use z to describe how far above or below the xy plane. So a lot of people call cylindrical coordinates polar coordinates in R3. And that's kind of okay. That makes sense. It has got a lot to do with polar coordinates. Okay. So not a lot to say about cylindrical coordinates. The polar coordinates are things that we've all just gotten through discussing. Z is just Z, so there's not much more to say. Okay, here's where it gets a little weird. This is spherical coordinates. Spherical coordinates is not just like polar coordinates. This is also sometimes, I think inadvisedly, referred to as polar coordinates in R3. I think this is a pretty significant mistake. It's got a little bit in common with polar coordinates, but nowhere near as much as cylindrical. So I think this is a brand new coordinate system, and we should just think of it as such. So anyway, here we go. We're going to define a direction first. The direction we're going to define by first. What is this angle? There's your polar theta. That's the connection to polar coordinates, granted. Okay. But that just defines an entire plane where in this plane are we talking about? Right, there's a lot of vectors in that plane. If I want to define specifically that direction, I need a second angle, and we use the angle as measured off of the positive part of the z-axis. We call that phi. That's the Greek letter phi. Let me write that down, by the way. So that is phi, lowercase phi. And between theta and phi, we have a direction defined. And once you have a direction defined, then we can talk about how far to go in that direction, and that is rho. And now do be careful with that. It looks a lot like a P. It is not a P. That's the lowercase Greek letter rho. Please don't write P. Students have a strong tendency to write P, but it's very importantly not a P. Okay, so this is going to sound a little weird, but you're going to have to kind of sit down and practice writing a new letter of a new alphabet, right? So maybe fill up a couple of pages with just make sure that you get to the point where you can draw it. There's a tendency for them to somehow turn into E's. That to me that looks like a lowercase e. So be careful with that. Right? And then again, sort of be careful that you don't inadvertently make a P. Okay. All right. Okay. All right. So those are the three coordinates of spherical coordinates, and it's another way to describe where a point is in space. Now, what's the algebra? How do these relate to rectangular coordinates? Well, there's a nice observation that you can make. Let's see here. So I'm going to use this right triangle there. Notice that this distance here is r, and therefore by the trigonometry of this yellow triangle, r is rho. Oh, by the way, this angle here is phi, right? So it is rho sine phi. And having observed that tells me, that goes a long way toward telling me what my rectangular coordinates are. I already know that x is r cosine theta. So r cosine theta, right? Y is r sine theta. And so I'm 2 out of 3 already there by the simple observation that r is something I can easily write down. I think it's a really neat trick, and I hope y'all will take advantage of that. Now z, okay, we do have to treat z a little bit differently. Well, z is, let's see here, z is this distance. And that's just an other side of this same yellow triangle, and so z is rho cosine phi. So make sure to know these formulas. These are the spherical coordinate conversion formulas. Something you got to know. Okay. Alrighty. So a quick observation I'll make, and then we'll move on. Again, there's a few other details to think about in this section, and think about read through and think about them. There's some exercises that'll have you think through some other aspects of coordinate systems. But I want to show you how to convert an equation from one coordinate system to the other. So, for example, this equation right here. Now we know that that's a circle of radius a, centered at the point a comma 0. Algebra 2, right? Ancient history, old high school algebra. Right? What if I wanted to describe that circle in polar coordinates instead of rectangular coordinates? What does that mean? What would that look like? And it turns out there's a really easy way to do it. All you do is plug in the conversion formulas. It could not be more direct. So we're going to take this x equals r cosine theta, right? And I'm just going to take that x and plug in our cosine theta. I'm going to take, for example, likewise, this x. Plug in our cosine theta. And let's see here. Now, y is r sine theta. Plug in y equals r sine theta. So see how I'm just straight plugging in the conversion formulas, and that gives me, it gives me an algebraic mess. This great big thing here is an algebraic mess. What is that in yellow? Great big algebraic mess. But I can multiply things out, capitalize on the Pythagorean identity there. Remember, sine squared plus cosine squared is 1. That's convenient, right? And after simplifying, here's a nice punchline. R equals 2a cosine theta. That is the polar equation of that same circle. Okay, and now here's that same argument again, slightly modified, taking advantage of the fact that, instead of, you can technically just plug in x equals and y equals and go to town, right? But here's the convenient lucky break that pops up sometimes. Instead of plugging in cosine and sine for x and y, if you should find that you have x squared plus y squared in your algebra, you don't need to mess with the cosines and sines. You already know that that's r squared. And that saves you a certain amount of algebra. And again, you can sort of compare, algebra-wise, which one of these looks uglier. And I like the second one a little bit less ugly. Everybody on board? Okay, so that's that section. That was a quickie. Okay, in fact, that's chapter 1 done now. We're going to move on to chapter 2. There's a bunch of stuff to do in chapter 2. Let's see here. How are we doing? Oh, we're good on time. Okay. We're going to talk about multivariable function. This is, after all, a course in multivariable calculus. We've done a bunch of stuff with vectors, adding vectors, operations on vectors, things you can build with vectors, different ways to describe vectors. Now let's talk about functions. Okay, first of all, what is a function? You'd be surprised how often this is misunderstood. A lot of students think a function is just a formula. Day in and day out, very often this is a relatively victimless crime. But it's not right. So let's be careful here just for a little bit. More strictly speaking, a function is a trio. It's not just a formula. It also has something called a domain and something called a target. So a function is this trio. The domain is the world of objects that go into the function, that go into the formula. Then there's this formula, right, and things from the domain. Here, let me label this domain. Put those things from the domain into the formula, and out comes something in the target. Right? So the function is a trio of all three of these things. It's not just the formula. Okay, and this ended up mattering sometimes in ways that we'll talk about when we get there. Okay. So here, for example, is a function. This is a function. The domain is R1. The target is R1. So this is a way of saying, look, into this function, I'm going to be plugging in any real value. This can take in any real value. And then I promise that what will come out is some real value. Okay. All right, and easy formula. You can see that does what I described. Now here's a slightly different function. This is a slightly different function. This function, as I've written it here, is only defined when x is between 0 and 1 inclusive. Well, that's not the same. That's what we had before. That previous function we talked about was defined for all real values. So a little bit different. Why we would care about such a thing? Well, situations arise. Okay. the promise that I'm making about the output values of this function. I promise that they will all land somewhere between 0 and 10, which is a slightly stronger promise than previously. I had only promised that what would come out would be a real number. Now I'm making a stricter promise. Okay, so a little bit different, even though the formula is the same formula. Okay, all right. Okay, all right. So let's look at a multivariable function. Here's a multivariable function. We're eventually going to be talking about the calculus of these kinds of functions. It's going to take us a little while to get there. We've got some more groundwork we need to lay first. But this is called a multivariable function because, and you'll notice there are 3 variables that go into this function, right? 3 input variables. So if I were to try to describe the domain of this function, I couldn't just say R1 because what goes into this function is not just a number. It's 3 numbers. So that's different. Okay. Now, it's not just that there are multiple input variables. In this case, there's also multiple output variables. So that is one of the values that comes out, and then you'll notice we have a comma, and that means that after this first output value, x plus y, there's another output value, 3xz minus yz. So 2 output variables. All right. So the clever observation in terms of how to talk about this is to observe that what goes in being 3 real numbers, I could think of those 3 real numbers as being the coordinates of a single vector that I'm going to call the x vector. You could give it different names. And so instead of thinking of this as 3 numbers going into f, I'm going to think of this as being 1 vector that goes into f. This is a vector that's in R3. So I'm going to think of the domain of this function as being R3, a 3-dimensional space. So this is a function that is defined on 3-dimensional space, kind of like what we live in. Does that make sense to everybody? All right. What comes out? Well, you can probably see this coming. These numbers I could think of as being a vector v. I didn't give names to these variables, but let's call them, p and q. It doesn't matter. Right? And this is a vector in R2. So I'm going to think of this as a function whose domain is R3 and whose target is R2, and we're going to write that like this. Here we go. F from R3 to R2. How are we doing? Is everybody on board? I'm going to use this notation a lot, by the way. So the heads up that what this notation means is I'm talking about a function called f. The colon says, now I'm going to tell you the other important things about this function f. That's the domain. The arrow says, now let me tell you what the target is. That's the target. Okay. All right. How do these have anything to do with anything? Do these relate to the real world? There's a bunch of examples of multivariable functions that are extremely natural, relatable things. I'm going to let y'all read most of these, but I'm going to talk about the first one. Let's talk about temperature. I claim that this very visceral experience of temperature that we all encounter in our everyday lives could be thought of as a multivariable function. And here's how that works. I'm going to think of the room that we are currently in as being a subset of R3. Let's say that over here in this corner, this bottom corner is the origin, x-axis, y-axis, z-axis. Right? Then this room is roughly rectangular. So this is a rectangular box sitting inside of R3 with those coordinate systems chosen like that. Okay, so here's the thing then. If you give me a point in this room, anywhere in this room, right, you're giving me an x, a y, and a z, Those are the inputs to this, what I'm going to call the temperature function. And the way I'm going to evaluate the temperature function is pretty straightforward. If you give me an x and a y and a z, I'm going to go to that point in the room, and I'm going to pull out my thermometer. I'm going to let it take whatever time it needs, and I'm going to measure the temperature there. That's the value, right? So the value of the function is the temperature, and pick your units. It doesn't matter. I don't care. So there are different temperatures at different points in this room. It's probably a little warmer up near the ceiling, usually is, right? A little colder in some corner, and there's probably a vent in here that's blowing onto somebody, making it cold, right? So it's significantly varying temperature in this room. That is described by a multivariable function like that. Yeah? Notice I didn't have to go to some obscure, deep, abstract, mathy, example to find a multivariable function. We're constantly surrounded by multivariable functions. It's really, really common. Okay. Very quickly, altitude as a function of longitude and latitude. That's a multivariable function. 2 numbers in, longitude and latitude. 1 number out, what's the altitude on the surface of the Earth at that point, etc. I'm going to let you all read the rest of these examples. Okay, how do we draw functions? This is how in a Calc 1 class you draw functions. You draw functions by drawing the graphs. This is called a graph. The idea of a graph is that with a function, here let me remind you, we're talking about a function from R1 to R1. Right? So there is an input variable, and we make that the horizontal axis, and then there is an output variable. We make that the vertical axis. And the graph is what you get when you consider all of the inputs and their corresponding outputs, and you plot the corresponding points. Okay, and we'll talk about that in a little bit more detail later on, not today. That is one way to make a picture out of a function. Please do notice, though, that functions are formulas combined with a domain and a target. Nothing in what's written down here said anything about a picture. So functions are algebraic objects. They are algebraic. Right? If you want to talk about it with a picture, you have to generate the picture. This picture is not intrinsically the function itself. Please separate in your minds. In a Calc 1 class, they're real sloppy about this because they can get away with it, and it's kind of fine in that context. But very important in this context, we need to separate the function as an algebraic object from this very, very different thing over here, which is a picture that we have drawn based on certain rules we came up with. This is a picture that helps us understand certain aspects of this algebraic object, the function. Right? But the picture and the function are different things. Now, graphs are great. There's a lot of cool stuff you can do with graphs. You'll notice, for example, there's connections between algebra and geometry here. The geometric feature of, the slope points down to the right is connected to the algebraic feature of, a certain algebraic construction has a value that is less than 0. So this is a geometric thing. This is an algebraic thing. Right? And connections between algebra and geometry are awesome. Super cool. Lots of good things can be done with those connections. Here's another one, another connection between the algebra and the geometry. Here it is. The concavity being up, that's a geometric statement, relates to this algebraic statement of, again, a certain algebraic construction, a second derivative has a certain algebraic characteristic of being positive. So there's another connection between algebra and geometry in the context of graphs. So the reason I want to point these out is in the process of recognizing that, look, this picture is not the function itself. This picture is just the graph. You've got to then further recognize that all these old rules that you remember about how do you think about derivatives and how do you think about second derivatives and stuff, those rules only apply to graphs. And what we're going to find in this multivariable context, we are going to find that we're drawing pictures that are not graphs. It's just going to end up being the case that we can't draw the graphs. I'm going to say not only sometimes, but usually you can't draw a graph. So if you're looking at a different kind of a picture and how that comes about, and we'll talk about that soon, right? But if you're looking at a picture that's a very different, fundamentally different constructed picture, it's not a graph, don't think in terms of connections that you've made to graphs specifically. Right? So for example, there's another construction we're going to talk about called level sets of a function. It's another way to have a geometric understanding of what a function's doing. The derivative being negative doesn't say anything about the slope of the level sets. It's really a very different thing. Okay, so be careful with that. Okay, so let's talk about this example here. I've got here. This is a different way to represent a function geometrically. I've got a function here from R3 to R2, and you'll notice that I've drawn the domain R3 over here on the left. I've drawn the target over here on the right, and I've plotted a single point in the domain, and then I've plotted its image over here in the target. That's definitely not a graph, all right? It is a picture of some sort, though. This picture is telling me some information about the function. This is a kind of an alternative to drawing a graph. It's arguably a poor alternative. Right? We're accustomed to, we're really spoiled, if you think about it. Graphs that we've drawn in single variable calculus classes, they show everything about the function. All the information about the function, it's right there. Oh my gosh. Spoiled, totally spoiled about that convenience. Not as good here, right? I can only see one input and one output. Let me point out, though, that we do have to make a fair comparison. If I want to compare this idea, this construction, with the graph construction, I should really be comparing this picture to, what would a graph look like for this kind of a function? What's the graph of this function f? Okay, all right. Well, let's think. Again, we'll talk about more details later. Remember, the idea of a graph is that you take the input axis and the output axis, and you put them on the same axis system, right? And then that gives you an axis system where you plug in certain values. Okay. Well, we had here one input variable and therefore one input axis. We had one output variable, therefore one output axis, and altogether then we had two axes and thus a two-dimensional picture to draw on our two-dimensional paper. And that's why it works out so well. It's just a match made in heaven. It is very convenient. What happens here? I've got three input variables. I've got two output variables. That means if I want to draw a graph of this function, I'm going to need to make an axis system that has 5 different perpendicular axes, and we don't live in a 5-dimensional world, and we certainly don't have 5-dimensional paper. Right? So we cannot draw a graph of this function. So don't think in terms of, I like these pictures better. Well, yeah, sure, no kidding. Of course you do, right? That's not the question. The question is, would you rather look at this picture or nothing? Because there is no way to draw the graph. Okay, so we're going to have to think about functions in, geometrically in different ways. And we're going to have to come up with a whole new set of rules of, what algebraic features of f tell you what geometric characteristics of what you're looking at here. We're just going to have to rethink that whole thing. Okay. And by the way, yes, sometimes in some very limited circumstances, we will talk about graphs. There's some cases where we can talk about graphs of a very small category of multivariable functions, and so I'm not jettisoning it completely. Okay, moving along. Let's talk about equations. First thing I want to take a moment. Let's recognize equation and function. These are very different things. Students all too often conflate these terms. This is a problem. Got to be really careful about that. Again, a function is a very rigid thing. A function is a formula combined with a domain combined with a target. A function is a trio of things. An equation is just a statement, and equations serve all sorts of different purposes. Now, yes, sometimes one of the things that I do with an equation is to describe the formula that is involved in a function. So, sure, equations are used to describe functions sometimes, but that's not what's going on here. Right here, I've got x squared equals 2x. I'm not telling you about some function. There's just some number x that I'm interested in for whatever reason, and here's a piece of information I might happen to know about that x, and then hopefully I can maybe solve for that x. I'm not talking about a function. See what I'm talking about? And then here's another one. This is not describing some particular value of x that I'm in search of. This is a sort of a general truth about how algebra works. This is true for all values of x. So this is, again, a very different use of an equation than either of the two previous. Okay. All right, so just want to point out, again, the big takeaway here is equations and functions are different things. So be careful, make sure to use the appropriate word depending on which one of those things you're actually talking about. If you're talking about don't talk about this function. That's not a function. That's an equation. Okay. All right. So solution sets, you all know what solution sets are, but just very quickly, if you have an equation, then numbers that you can plug in that make the equation true, we call those a solution. Now do be careful. Here, let me zoom again. Do be careful. It's tempting to, if you think back to equations that you've solved in the past, the solution has been a number, or a solution has been a number. Note that's not the case here. Here, a solution to this equation is a pair of numbers. It's a point in the xy plane. Keep that in mind. Okay. On the other hand, it is going to happen sometimes that you try to plug in some other values, like if you take these values, this is a different point in the xy plane, you plug that in and the equation fails. Right? So that's not a solution. Okay. Some points are solutions, some points are not solutions. The solution set is the collection of all of the solutions. Right? And there might be lots of them. Geometrically, this is pretty easy to see. Let's look at this equation right here. Here's an equation, right? And I can draw a picture of its solution set. Its solution set is an entire line. Right? There's lots of different ordered pairs x comma y that satisfy that equation. Okay, so usually, if you have an equation, the set of solutions is a shape of some sort inside of the appropriate space. Now this is an equation that involves two variables. That means that its solutions live in R2, and the shape is a curve in R2. Everybody happy? Okay, so what if we want to step it up a notch to 3 dimensions? So for example here, let's look at that. Highlighter. Let's look at that equation. Tricky, right? What is that thing? Some people will say, well, it's a parabola. Well, no, it's really not a parabola. There's 3 variables there, right? So solutions to this equation are points in 3-dimensional space. So this is not a curve. This is going to be some sort of a surface. Some people say, oh, it's a circle. Look, I see the x squared plus y squared. That means it's a circle. Nope, still a curve, right? So exactly what kind of surface this is and how does this relate to circles or parabolas or what, that's something we need to be more precise about. Okay, so now there's several techniques that I'm going to show you all for how to identify, given an equation, how to sort of piece it together. What kind of a surface is this? This first method is a little tedious sometimes, but it has generally works out pretty well. But I'm going to show you some trickier tricks later on. We probably won't get to those today. We'll see how this goes. But I'm going to start off by revising the question. So we have this equation. I want to solve that equation, and I'm going to say, let's suppose I have more information. Let me cheat and say, I would like to pretend that not only do I know z equals x squared plus y squared, but I would like to pretend that I also know that y is equal to c, some constant. Nice, convenient little constant. Isn't that nice? Now, cry foul, of course. You can't just do that. Right? And, well, point of view. He says, right, I can't do that. What I can't do is assert that y is equal to c and never come back and address of what I've done. Right? That is against the rules. But it is perfectly reasonable, perfectly legal, and there's a long tradition of this in math, of just viewing special cases. Right? Understand special cases of a problem first. And with full confession that what I am looking at is only a special case. And then once you understand a special case and maybe another special case, lots of different special cases, then try to piece it all together and see, okay, now let's consider the full question. Right? So that's what we're really doing here. This is a special case, and I'm acknowledging that as such, so this is perfectly legal. And now let's think about what I've got here. This is a mystery surface. I don't know what that is, but I do know what this is. Y equals c. That's a plane. Right? Okay, so what I'm looking at here is the collection of points that are on my mystery surface and that are also on this plane that I understand very well. So here's another way to say that. I'm looking for the intersection. This is the intersection of my mystery surface with a plane that I understand very well. And good news, I can do a lot with this algebra. Right? I can take take this y equals c and stick it into there, and then that turns into this. And that is something that I do understand. Right? That is, no kidding, absolutely a parabola. Z equals x squared plus some constant. For sure, 100% parabola. Okay, so what that means then is that if I think, so I've got this mystery surface. I don't know what the mystery surface looks like, but if I look at a slice, if I look at its intersection with this plane, let me say that a little bit differently. If I look at a cross section of my mystery surface in that plane y equals c, that cross section is a parabola. And that's a lot of information. Got the picture down here. I guess I can't quite squeeze that in there. Let me do like this. So in this plane where y is equal to c, my cross section is a parabola. Okay, now a couple of details. Notice that, where the, I didn't draw that very well, did I? Here, let me try to draw that plane a little bit better. In this plane, that point there, that's where y is equal to c. Right, that's the plane that we wrote down in the first place, y equals c. And now, where'd this parabola come from? I've got that parabola shifted up a certain amount, you'll notice. Well, the amount that it's shifted up, you can see right there, the shift is c squared. Right, so that, sorry, my elbow keeps hitting that thing there. This upshift there is c squared. And now I appeal to your geometric intuition. So cross sections like this give me parabolas, but I can do that cross section kind of anywhere. I mean, c could be over here, it could be negative, c could be 0, c could be larger and larger, whatever. All the parabolas aren't going to look the same. The parabolas are going to be shifted up by some amount, c squared. And so as you come away from the xz plane, as y increases, as therefore c increases, the shift, the upshift, is going to be the square of how much I've pulled away along the y-axis. Right? And so that's why I've drawn here. You'll notice that this upshift is a lot bigger over there, where c is larger. Right? There's a larger value of c there, and so the shift is quadratically larger. Okay, and then likewise, again, my elbow always hits that. Sorry, like that. Okay, so we've got a lot of information about our mystery surface at this point, right? We know what all the cross sections look like perpendicular to the y-axis. How are we doing? Is everybody on board? Okay. And now we have this artistic, visualization challenge of, given all these cross sections, how do they, take all these cross sections, interpret in the appropriate planes, suspended in space where they're supposed to be, and now glue them all together, and what do you get? It's hard, right? By the way, drawing this picture, a little hard. There's things to know about how to draw these kinds of pictures, and that's something that we'll talk about as we go along. So I'm going to look at this from other angles as well. So we could, for example, we could look at cross sections. Oh, let me go back to a different color here. We could look at cross sections where we set x equal to a constant. That gives us different parabolas. These are perpendicular to the x-axis. And that gives me this alternative picture, which again, this is hard to draw, but in some plane over here, right, there are cross sections that are parabolas. And the upshift is again quadratic in the value of x. Also, you could take cross sections perpendicular to the z-axis. Set z equal to c. That gives you these equations, not parabolas. That gives you circles. C is positive. C is negative, you don't get anything. Swing and a miss, right? If c is negative, a negative number can't equal to the sum of two squares. Okay. But so in horizontal planes, where z is equal to c, the cross sections are circles. So now we have three different sets of pictures here, and it's a lot to piece together, but I think you can probably think it through and persuade yourself that we're talking about a bowl shape here. This is called a paraboloid out of respect for the parabolic cross sections in two of the three directions. Everybody happy? All right, so this is the method of cross sections. You can apply this to different shapes. Let's consider real quick this one here. Z is equal to x squared minus y squared. Now that's different. X squared minus y squared. Well, if you set y equal to a constant, notice we're going to have parabolas that are shifted downward. They're upward pointing parabolas in the x direction, but they're shifted downwards because we set y equal to a constant. Or you could do it the other way. You could set x equal to a constant. With x having been set equal to a constant, let me zoom in for focus. Set x equal to a constant, then you have downward parabolas, downward cross-section parabolas. But they're shifted upwards because x is what's been set equal to a constant. So that's hard to visualize, right? But draw the pictures, and again, they're hard pictures to draw too, right? But all together, here, you get something like this. So here are the upward pointed parabolas that shift downward. Right? Here are hard to draw downward pointing parabolas that shift upward in the perpendicular direction. And you got to again, really think about the geometry of this, and what you end up with is it looks like a Pringle. Everybody kind of see that? By the way, you could also think about the z cross sections to this. What happens if you set z equal to a constant? Well, y'all recognize these as hyperbolas, right? I hope y'all remember your Algebra 2. By the way, I am assuming that y'all are all crisp with your Algebra 2. It's important. It just doesn't go away, so make sure you're good with that. And you can see those hyperbolas in the cross sections here. Think about how, if you had a Pringle, and if you were to just take a nice sharp cut through a Pringle, well, you would get, again with the elbow, you would get kind of a cross section like that, and a kind of a cross section like that, and there's your hyperbola sitting inside of that horizontal plane. Everybody happy? Okay. All right. So let's see here. Where are we now? Yeah. Okay. So there's other examples. I'm going to let y'all look at those other examples yourself. I'm going to draw the line right here for today. We will pick up here on Monday. Y'all have a good weekend. See you later.